There you go. Okay. Determining the scalar equation of the plane. So what you see there on the screen is a plane. And there's a vector, or two of them, in fact. So there is a direction vector pointing from a known point on the plane P0, okay, to any other point on the plane. And you'll see a blue vector, which is 90 degrees to that vector, okay? Now that blue vector, it's called a normal vector. And we saw normal vectors when we did equations of lines. So if you recall the equation of a line, so recall the equation of the line is ax plus by plus c equals 0, where a and b represent the normal vector to that line. Okay, and visually it looked like this. So you had a line and you had a normal to that line, 90-degree vector, and that was vector n. Okay, so and we got a scalar equation from that. And the same way we did that for lines, we do that for planes. We need a normal vector to the plane. Okay, and we're going to use the same notation n. Just this time, because a plane's in 3D space, we have to have that third component, the A, B, capital A, capital B, capital C. So that stands for the x component, y component, and z component. And once you have the normal of the plane, you can define the scalar equation of the plane with something that looks very similar to the one for lines. If I scroll down a bit here. So the development of the formula through the dot product between your vector on the plane, P0 and P, and the vector n, the normal vector, that dot product is equal to 0 because they are perpendicular to each other. And then from that, you can develop the equation, the scalar equation of a line. So I'm just going to highlight the end result. And the end result is the scalar equation of a line is this. A times x plus b times y plus c times z plus a constant d equals to 0. Okay, so c is no longer that constant. C is the z component of the normal, and d is that constant at the end. This is what defines a plane in terms of talking about scalar equations. Okay, so you need that normal vector. So that's like different from the vector and parametric. The vector and parametric did not have the normal vector. It just had the two vectors and a point. Okay. So how do we find the scalar equation? So here's the first example. Find the scalar equation of a plane which contains the points A, B, and C. So these are 3 points, not to confuse them with the normal vector. So not to confuse. These are coordinate points. So these A, B, and C are not part of the normal vector. Okay, these are just coordinate points, which we can turn into point vectors, which we can turn into direction vectors as well. Okay. All right. So scalar equation of the plane. If I need a normal vector to define the scalar equation, right? The normal vector. To get a normal vector, well, think about what a plane has. So if a plane has, let's draw a picture of a plane. Here's a plane. And I'm going to define 3 points on that plane. Let's put 3 points anywhere on this plane. Let's say these are the points A, B, and C. Okay. Now, if I was trying to get the vector equation of a plane, then I would need to create 2 vectors. I could create a vector from A to B. Okay. And I could create a vector from A to C. Okay, and if I had those 2 vectors, I could write out the vector equations of the plane. Now with the scalar equation of the plane, I need the normal. Okay, I need a vector that's normal to the plane, that's 90 degrees to the plane. So you're going to have to reach back to one of the tools we used in chapter 7 that allows me to find a vector that is both 90 degrees to these other 2 vectors that are also on my plane, right? So if I could find a vector that's 90 degrees to these 2 red vectors, then I know that normal vector is also perpendicular to the whole plane, okay? So what tool do we use to do that? cross product. Okay, so here we're going to write to find n. I need a vector that is 90 degrees to my planes, apostrophe s, direction vectors. Okay, so what we're going to do to do that is we will use the cross product to find n. There we go. Okay. So here's where we start connecting concepts from the previous chapter. So cross product is the one of the three multiplications you can do with vectors, that the result gives you a perpendicular vector. Okay. So I need to find the cross product to find n. So I'm going to say here n, normal vector n, is the cross product between, let's call these vectors AB crossed with AC. Okay. And so I need AB and AC. And I can find them because I am given the points for A, B, and C. So I'm going to, here on the side, I'm just going to write here AB, the vector AB. I can create that by looking at the subtraction between the components between points A and points B. So -1 minus 3, which would be -4. 5 minus 4, which is 1 for the y component, and -7 take away -2, which is -5 for the z component. Okay. And I'm going to create a vector from A to C. And that vector is, if I subtract the components, looking up here again, 3 take away 3 for the x, which is 0. And then we have -2 take away 4, which is -6. And -1 take away -2, which is +1. These are my two vectors for AB and A to C. And then from these two vectors, I can find the cross product of them to get my normal vector. So the cross product of AB cross AC is going to just write out my method that I usually use. So here I'm going to write the first vector on top. So -4, 1, and -5, -4, 1, and -5. And the second vector below it, 0, -6, and 1, 0, -6, and 1. So that's how I'm setting it up. If you recall, cross out the first and last column. And then we're going to be cross multiplying and subtracting. So the first component, the x component, is going to be 1. Take away -6 times 5 is 30. The y component is going to be -5 times 0, which is 0. Take away 1 times -4, which is -4. And -4 times -6, which is +24. Take away 0 times 1. Take away 0 for the z component. And then simplifying, I get -29 for the x component, +4 for the y component, and 24 minus 0, which is 24 for the z component. So there's my vector n, the normal vector to my plane. Right? So I know that that vector is perpendicular to AB and AC, so therefore it is perpendicular to the plane because AB and AC lie on the plane. Okay, and then once you have the normal vector, the equation for the plane, you just have to remember this general form is ax plus by plus cz plus d equals 0. You plug in the a, b, and c. So from a normal vector, this is -29 is the a, +4 is the b, and 24 is the c. Okay, so -29x plus 4y plus 24z. We don't know what d is yet, so I leave it as d equal to 0. And just like the equation, the scalar equations of a line, the same process you use to find that unknown constant, which is I take a point that I know that's on the plane and sub it in. And I have 3 points. I have A, B, and C. I have 3 known points that are on my plane. And so I'm going to take any one of them, anyone, arbitrarily choose one of them. So if I pick I could pick point B. So if I pick point B, I'm substituting in -1 for x, plus 4 times 5 for y, and then 20 plus 24 times z, and z is -7, plus d equal to 0. And then you expand and simplify, you collect, well, you simplify and you bring all the terms over to one side, solve for d. The answer you get is 119. And then when you put that back into the equation, you get your equation, -29x plus 4y plus 24z plus 119 equal to 0. There's your scalar equation. So on the next page, just one more example with 2 parts to it. Find the scalar equation of a plane. That is, so instead of giving you 3 points, maybe you get vectors, maybe you get something that you have to infer a vector from. And so here you have an equation of a plane that is parallel to the plane, to another plane that's given to you as a scalar equation, and includes the point 5, -7, and +8. Okay. So you look at this equation of the plane, you think, oh, what information does this plane give me or give you? I can read a normal vector to this plane, A, B, and C, right? So I can read there's a normal vector here of -3, 2, and 5, okay? And then I go, okay, if the plane that I want, okay, so let's say I had the plane, this is the plane I wanted, okay, and it's parallel to another plane. Maybe it's set higher or lower, okay. That normal vector to that plane, I'll draw a vector like this. So here's a normal vector. That normal vector to that plane is going to be the same normal vector from the plane that I want, okay. So for 2 planes that are parallel, the direction of the normal vector of both planes are the same. Okay, there's no way you can get 2 parallel planes that have a different normal vector pointing in different directions. They have to point in the same direction. So the normal vectors for parallel planes are the same. Normal vectors for parallel planes are the same, okay? Or they could be scalar multiples of each other too, okay? That's also a possibility. But for the purposes of this question, you can just take the same normal vector and write it as the one for your new plane. So the plane that we're looking for, the new plane that's parallel, is going to be -3x plus 2y plus 5z, okay? However, the constant is what we don't know, and we cannot assume that it's 8, right? If we said 8, then we are essentially creating the same plane, okay? So all that we know is that it's not going to be 8. It's just if it's a parallel plane that's not coincident, it's not the same plane, then that 8 has to change, okay? So what we do know is that we are given a point on the new plane, okay? And if we're given a new point, we're going to sub it in. So sub in 5, -7, and 8. So if I substitute that, I get -3 times 5 plus 2 times -7 plus 5 times 8 plus that constant that we have to solve for, okay? And then we have -15 plus, oops, or minus 14 plus 40 plus d equals 0. And if you add up those terms and you solve for d, d is equal to -11. Okay, and so we get -3x plus 2y plus 5z minus 11 equals to 0. Okay. as the equation of the plane. So very similar to the parallel planes, because they have the same normal. It's just that one has a +8, the other one is a -11. So they're kind of spread apart.
Is it positive 11?
Positive 11, positive 11. -40, no, unless I did something wrong here. D equals, you bring the 40 to the other side, it's -40, right? And then +15, +14, that's 29. 29 minus 40 is -11. Unless I got these numbers wrong, which I don't think I did. Okay. Okay. Part B. So here's part B. So we want a plane now that's contains the following lines. We're given a vector equation of a line. So that's important to notice. If it only has one parameter t or s, it only has one parameter, it's a vector equation of a line. If you start seeing a point vector plus a direction vector with a scalar plus another direction vector with a scalar, that's an equation of a plane. Okay, so it's important to recognize that this is a line and not a plane. Okay, sometimes it's easy to confuse that when you're going back and forth between lines and planes. So I want a plane that contains the equation of this line, or that has this line rather, and it's parallel also to the line defined by the parametric equations, which are not written there. They are x equals 5 plus 3s, y equals 1 minus s, and z equals 2 plus 4s. Okay. So let's call the vector equation line 1. And these set of parametric equations are line number 2. So let me zoom in there like that. Chelsea.
What can we get those numbers from?
Just pretend they're part of the question. I just forgot to type them.
Oh, okay.
Yeah, these are part of the question. Part of the question. Part of the. They just got erased probably or something. Yeah, part of the question. Given. These are given. Okay. Okay, because if I didn't give you that, then you'd only have one line, and then how do I create a plane from one line? So as I said, actually this actually highlights the point that if I have a plane, to define a plane, I need two vectors. Okay, and if I know a point, I know a point. So I need two vectors, and the point could be there, it could be anywhere really. But I need two vectors, and the two vectors I'm going to get them from I'm going to get those two vectors from the direction vectors of each line. So if I only had this one direction vector, 3, -2, and 1, I'd be lost. I couldn't find the equation of the plane, right? Like one direction vector pointing in space, the plane could be anything. Could be here, could be oriented this way, could be this way. Like one direction vector is not good enough. I need two to define the plane. So which is why I'm giving you the second equation of a line. And it doesn't have to be in vector form. It could be in parametric form like this, okay? But from each form, I can extract that direction vector and use it. So for the plane, let's write it, I'll write it down here. For the plane, I need two direction vectors. So if I have M1, I'm going to just take that from the first vector equation. So that's going to be 3, -2, and +1. And the second direction vector for my plane, I'll take that from my set of parametric equations. So you have to remember, or kind of have to know how to read these parametric equations. So if you recall, if I had converted from a vector equation to a parametric, or are you still copying? Sorry. If you had converted from a vector to a parametric, these three numbers would be from your point vector, okay? And it's a direction vector that'll be attached to that variable s, or the parameter s. So I'm going to be reading this number for the x, and this number for the z, and the y number is just the invisible 1, okay? So the direction vector is going to be 3, -1, and +4. So 3, -1, and +4. And this is from the coefficients of the parameter in the parametric equations. Okay. Okay, so I have the two direction vectors that I need. Then you think about, okay, I have two direction vectors, I can define a plane. And then, okay, if I have that, then the scalar equation of the plane, remember, you're trying to find a scalar equation. I need a normal vector. I need a vector that's perpendicular to that plane. So that vector is going to be represented by n. And the only way I could find it is just by taking the cross product of my two direction vectors, right? So these two direction vectors are going to be defining the direction of that plane, and then, which means any cross product will be automatically perpendicular to those vectors, which is perpendicular to that plane. And yeah, and to illustrate, so remember, cross product perpendicular to each vector, which means it's perpendicular to the plane. Okay, let's do the cross product. So here I have 3, -2, 1, 3, -2, and 1. And the second vector is 3, -1, and +4, 3, -1, and +4. Scratching out the first and last columns, cross multiply and subtract. So here I have for my vector n, it's going to be -2 times 4, which is -8. Take away -1 times 1, which is -1. That's for the x component. For the y component, I have 1 times 3, which is 3. Take away 4 times 3, which is 12. And then for the z component, 3 times -1 is -3. Take away 3 times -2, which is -6. So always be careful with the inevitable double negatives that pop up. You don't want to make a mistake with the signs, because then you'd throw off everything, the work. So here we have -7, and then -9, and +3 for the normal vector. So -7, -9, and +3, from which I can put this into the scalar form of the equation. So -7, so scalar, let's write scalar equation, -7x minus 9y plus 3z plus d equal to 0. Okay. So the missing component here is, what is that constant value? And for that, I need a point on the line, or point on the plane. Okay. Do I have a point on the plane? Go back to the question. Doesn't give you one explicitly, okay? But you're told the plane contains that line with the vector equation. And if I read that vector equation does contain a point vector for -3 and -2. So if that point is on that line, and that line is on that plane, then that point is also on that plane, right? Logically, right? So I can use the given point. So use the point for -3 and -2, which is on both the line and the plane. Okay, and then, okay, let's put it in. -7 times 4 minus 9 times -3 plus 3 times -2 plus d equal to 0. And then if I solve, let's see if I can do this right. So -7 times 4 is -28. 9 times 3 is +27, and then -6 plus d equal to 0. And so d is equal to -1 minus 6 is -7, which becomes +7 on the other side. So d equals +7. So therefore, the equation of the plane is now complete here. So -7x plus 9 or minus 9y plus 3z plus 7 equal to 0. So be careful again with that. That d is +7, it's positive in the equation. All right, so that is it for the scalar equation of a plane. And because I'm recording this, I'm just going to say like and subscribe as it goes up on YouTube. There you go.